Well, good morning. First of all, I'd like to thank Yoho for his very kind introduction. And of course, it goes without saying that I'm extremely honored and very happy to have been awarded the Millennium Technology Prize. It certainly has a wonderful pedigree over the last 10 years of having chosen some really outstanding scientists who have strongly influenced our lives through their innovations. What I'd like to do today is tell you something about my own work for which the prize has been awarded, and this involves this new field called Spintronics, or how we introduce the electron spin into electronics to create new devices for memory and computing applications. So what I'd like to do in this short introduction is briefly discuss how we can take artificially engineered materials, which you can see here. If this works, let's see. Well, you can't really see. But anyway, artificially atomically layered materials with which we can engineer properties that are useful, for example, for storing data, digital data, in a variety of ways, which I'd like to discuss. So let me just say something about who I am, although Juha has already mentioned this. So science today is a very global enterprise, and I'm very fortunate to have been brought up in England and have spent my early part of my research career in Cambridge and in Paris. And as a kid, I was always motivated to go to Cambridge because of Isaac Newton. You probably have heard of, one of the greatest scientists who have made such enormous influence on the scientific revolution. And he was both a student and a fellow at Trinity College, as I was. And there I'd like to particularly mention Richard Friend. It's very important to have mentors, and I had an excellent mentor in Richard while I was a student, a PhD student at Trinity. Then I moved to Paris, to the University Paris-Sud, and there I worked in the group of Denis Jerome on some very interesting new materials, some organic materials that would become superconducting at low temperatures. And those materials are very, very exciting. In those days, 20, 30 years ago, it was believed that you could engineer some organic materials that could be superconducting at temperatures even as close as room temperature. And that's still a significant interest of mine. And that was the reason that I moved to IBM to work in the group of Rick Green on these materials. So I moved from Cambridge to Paris, and then you can see here, San Jose, California. This is my house. It's a beautiful place to live and to work. It's the capital of Silicon Valley. And so there are a lot of the developments that have taken advantage of digital data have taken place over the last 10 or 15 years. And here I've just included a picture of my fiancée, Claudia, who's in the audience. And she and I have a lot of common interest in materials. And it's the reason that, as mentioned by Juha, I'm actually moving to Germany next year. But let me say something about Cambridge, IBM. IBM has 12 corporate research laboratories around the world. And I have been working for the last 30 years in the corporate research lab in San Jose, California, in a part of the city called Almaden. It's a beautiful valley. And you can see here a picture of the IBM research laboratories, which is on top of a hill. In those days when the lab was built, it was believed the scientists should be isolated from everybody else so we could think. But I think today, this is exactly the opposite way we do science. It's really by communication and intense interaction with colleagues around the world that makes scientific developments possible and are indeed accelerating. And again, my interest all this time has been in the development of new materials which we can essentially create unnatural materials by building them a single atomic layer at a time. And you can see in the bottom right-hand part of this foil a system that I built over the last 10 years. It's probably one of the most sophisticated systems we like to believe for developing thin film atomically engineered materials. And in this system, we could use up to 80 different elements to create new materials. I'm going to come back to this a little bit later. So IBM certainly has been a great place to work in terms of doing fundamental science that could impact technology in the longer term. And so let me make a couple of comments about innovation in a moment. As I mentioned, I'm actually moving to Germany to the Max Planck Institute for Microstructure Physics, which is in Halle. And at the same time, I was appointed a professor in the Martin Luther University. So this is by way of an advertisement. Any of you who might like to carry out science in Halle, please think about this. We have PhD studentships, postdocs, and junior group leader positions available to work on some of these new materials. So maybe just by way of introduction, what really is innovation? And one has to distinguish innovation from invention or scientific discovery. And we like to think of innovation as where one takes important or interesting scientific discoveries, appreciates how they could be used, and how, in particular, we can create some value to society, impact society in significant ways. And this is really what innovation is all about. And for me, as a scientist, it's extremely exciting when one can take fundamental new understanding and discoveries and understand how one could take those discoveries and impact society in some period of time. And by working at that intersection of science and potential technological application, this is extremely exciting. And today, I think there's a lot of innovation that is taking place. And indeed, if you look at how innovation is being introduced into society, we can see that it's really happening very rapidly. And innovation, in many ways, is accelerating. One way to look at that is simply by the speed of the introduction of new technologies into the marketplace. What is the market penetration? So it took more than 100 years before most of us had access to a telephone or an automobile. But in the past 10 or 20 years, innovation has really accelerated, and many of us have rapidly been able to have access to the internet, have access to a personal computer, and more recently, many of us have cell phones, and the penetration of cell phones has happened incredibly quickly in just a small number of years. So in many ways, innovation and access to new technologies is indeed accelerating. And that's because of fundamental discoveries that we made in science, and particularly in new materials and new fundamental physics or chemistry that enables these new technologies. So if we look back in time, though, a very important innovation was by Johannes Gutenberg. And what he did was he invented a method of printing a book using movable fonts, movable type. And he essentially invented a printing press. So before his innovations, it was only possible to read, only tiny numbers of people had access to books, because these books had to be prepared by hand. And what he was able to do was introduce a technology that enabled, in some sense, the mass production of books. It wasn't tiny numbers, but significant numbers that enabled more people access to knowledge. And that, in some sense, was the beginning of the Age of Enlightenment. Well, that was 550 years ago. Now, in those days, then, books were an analog technology. There were many, many different letters were used to represent the information recorded in a book. But 50 years ago, in some sense, the way of storing that information, in some sense writing books, became digital with the introduction of digital data storage. And in fact, this was an innovation that IBM introduced themselves in the 1950s. So for about 50 years then, we've had access to the ability to store information digitally. And the way that works is we store information as a series of magnetic regions in a magnetic film. And this is shown here, but you can't really see, but if we look here then, you can see here, this is a magnetic layer, and these are magnetic bits, regions of magnetic material magnetized in one direction or another, and the boundaries between these magnetic regions are where we store the zeros and ones as the presence or absence of these boundaries. And you can see in this picture on the bottom left how these magnetic regions have been shrinking over time. And a few years ago, it became increasingly difficult to read those tiny magnetic regions. And this is what my work enabled, the possibility to read magnetic regions that were 1,000 times smaller than was possible with the technology at that time. So we are storing information now as simply the presence or absence of these magnetic boundaries in other words, as zeros and ones. And this is a digital data storage. And you can see that this information is stored in these devices shown in the middle portion of this foil, a magnetic disk drive. And today we would have hundreds or thousands or tens of thousands of these magnetic disk drives to store information, typically in the cloud, and you access it through modern communications. And this is what we like to think makes possible Facebook and Google and Twitter and Instagram, Dropbox, and of course WhatsApp. And of course these new businesses are incredibly valuable. So for example, many of you might know that WhatsApp was just bought by Facebook for $19 billion. That's a lot of money. So it's amazing the incredible value that has been created in just the last 10 years because of our ability to store information and knowledge digitally. And this is only made possible by Spintronics, as I would like to now try to discuss in more detail. So first, though, let's look at how the information that is stored, how this has evolved over the last 2 decades. So this is a chart that shows the total capacity for storing digital data with all the devices that have been made in the world. And you can see on the left-hand side, this is the number of megabytes, the number of digital bits that can be stored in all of these devices as a function of time, and this number is increasing very rapidly, exponentially. But more importantly, the type of devices we use to store that data has undergone a dramatic transformation in just the past decade. And those devices have changed from an analog form, such as books, to a digital form. And you can see this in the technologies which are analog are shown in orange, and the pie chart shows you the different types of technologies that are used to store these data. And in the last 10 years only, that data now is largely stored almost entirely digitally. So we've eliminated books and many other forms of conventional analog forms of storing to replace them with digital forms. And this analog to digital evolution means we've gone from books to hard disk drives, where nearly all information today is stored. So the ability to store information in using magnetics is a very, very old concept, and of course it's used biologically, but one of the earliest forms of storing magnetic data was shown here in what was called a magnetic core memory, a very, very interesting technology where one used rings of magnetic material, and the information was stored as the direction with which the magnetic moments were aligned around this annulus. Whether they were aligned clockwise or anti-clockwise represented a 0 and a 1. And to store a read and write information into these magnetic rings, current was passed through wires that were passed through the middle of these rings, both to write and to read information. This type of technology then really couldn't scale to small enough dimensions, so it was a very short-lived technology, but nevertheless a very interesting one. And this was replaced by magnetic hard disk drives. So let me now tell you something about Spintronics. So today, most computing devices simply are based on using electrons and using the charge of the electron. We store a number of electrons in a capacitor, or we monitor the flow of currents of electrons and their charge in transistors. And this enables us to build both memory and logic devices. But the electron possesses a very important quantum mechanical property called spin, and the spin of the electron just takes 2 values. It's either spin up or it's spin down. And this is essentially all that one needs to know to understand the fundamentals of spintronic devices. And let me try to explain this in the next few foils. And by the way, you can see here on the right-hand side this cartoon. This is IBM logo in the form of electron spins. And IBM is a company that was 100 years old 2 years ago, and it basically represented its 100 years of progress by 100 of its most important technologies and innovations, and one of these was Spintronics. So if we take a non-magnetic material like copper, and we introduce current from a battery, then the current will be comprised of electrons and their charge, but the electrons have spin up and spin down. So there will be equal numbers of electrons with their spins pointing up, and equal numbers with their spins pointing down. The current itself will possess no net spin polarization. This is in a non-magnetic material like copper, through which most current is passed today in, for example, logic and memory devices. However, a very interesting discovery was made in the 1930s by Neville Mott, a very famous Nobel Prize-winning scientist, also from Cambridge. And what he realized was that if you pass current from a battery with equal numbers of spin up and spin down electrons into a magnetic material, the current is carried by electrons with one spin polarization predominantly. So within a very short distance of the introduction of current into a magnetic material, the current will become so-called spin polarized and consist of electrons, of course with their charge, but with their spins pointing in the same direction. And now we can manipulate the currents of these spin polarized electrons if we build structures on the atomic scale involving both magnetic and non-magnetic components. But first, let me point out what this meant. In 1988, Albert Fert and Peter Grunberg discovered a very interesting phenomenon which Albert called giant magnetoresistance. And this was in a very interesting form of a magnetic material which they had engineered, in which you had very thin layers of magnetic material iron separated by very thin layers of a non-magnetic material chromium. These are metals. And in a superlattice of alternating iron and chromium layers, they discovered that when they applied a magnetic field, the resistance of this structure would drop quite dramatically at low temperatures by almost a factor of 2. This is shown in this curve, which is the resistance of this multi-layered system as a function of the applied magnetic field. And in zero field, for a certain thickness of chromium, the magnetic iron layers are oriented anti-parallel to one another. But when a sufficiently large magnetic field is applied, these moments become aligned in one direction or the other direction, and the resistance dramatically decreases. This is what is termed magnetoresistance, and this is a giant change in resistance, so giant magnetoresistance. And Albert and Peter won the Nobel Prize in 2007 for this discovery. From a technological point of view, this was a very, very interesting scientific discovery, but at the time it wasn't clear as to whether or not this could be used technologically. The materials they used were grown by rather exotic thin film deposition techniques called molecular beam epitaxy. The effects were largest at low temperatures and required enormous magnetic fields to see these changes, much too large to be useful, for example, for magnetic disk drive applications. They also showed that the phenomenon decreased monotonically as the chromium thickness between these iron layers was increased. So I was very interested in this phenomenon, and in 1989 or 88, I attended a conference in France, in Le Creusot, where Albert gave a talk about this discovery, and it prompted me to see whether or not I could see the same phenomenon in materials made in a very different way using a technique called sputter deposition. And I'm going to discuss that briefly in the next few foils. And then actually the three of us were awarded honorary doctorates from the RWTH Aachen in the same year. So what I was able to do then was to show that giant magnetoresistance could be observed in a whole variety of thin film structures. And the effect could be extremely large even at room temperature by changing the materials from iron to cobalt and from chromium to copper. And this is a similar graph of my own work, which shows at room temperature one could see changes or drops in resistance of a factor of 2 in, again, very large magnetic fields if one uses these magnetic multilayers, magnetic layers separated by atomically thin copper layers. And I showed that this phenomenon was actually rather general. One could see it in a whole variety of metallic multilayered systems, although the effects were largest when one uses these particular materials, also showed that the phenomenon, the origin of this effect, is largely related to the interfaces between the magnetic and non-magnetic layers, which was very important technologically. And at the same time, these materials, I could show we could use very simple methods of preparing them using a phenomenon called sputter deposition, which is a technique one could use for mass production of these materials. So this is a system, one of my thin film depositions systems at IBM, in which I've carried out some of this work. And as I said, this means because we could use this technique for preparing these films, we could explore a whole variety of materials. And in the following years, we prepared approximately 100,000 different thin film structures to try to understand the origin of giant magnetoresistance and related phenomena. And what was really amazing was that we could actually use this technique of deposition to prepare structures where the individual layers could be controlled down to a single atomic layer, and we could see that would strongly influence the properties of these films. And we could do that in mass production. So if we go back to what happens if you introduce a current from a battery into a magnetic structure, let's look at a sandwich of two magnetic layers separated by copper. And in this case, let's look at what happens if we have two magnetic layers with their magnetizations pointing in opposite directions, separated by a thin film of copper. When we introduce a current from a battery into this sandwich, then in one of the magnetic layers, the current will be carried by electrons of one polarization, one spin polarization, and in the other magnetic layer by electrons of the opposite spin polarization. And what this means is that in this sandwich, electrons of both spin polarizations will be strongly scattered in one or other of these magnetic layers, leading to a higher resistance. However, if we now change the magnetic orientations of these layers so the moments are oriented parallel to one another, then in this case, electrons of one spin polarization will not be scattered in any part of the structure strongly, so the resistance is lowered. And so we call this type of sandwich structure a spin valve, which means that we could turn on and off the flow of this current of spin polarized electrons simply by manipulating the magnetic orientation of these layers. When the layers are parallel, the resistance is low, and when anti-parallel, the resistance is increased. And this then leads to this concept of a spin valve magnetoresistance. And in this case, the change in resistance is smaller than in a magnetic multi-layer system, but it's only 10 times smaller at room temperature, but the magnetic field required to develop that change is 10,000 times smaller. So we have a device that now is much more responsive to tiny magnetic fields. And this sort of device is one of the world's most sensitive detectors of small magnetic fields at room temperature. We can detect fields that are much smaller than, for example, the Earth's magnetic field, through the change in resistance of this structure in response to the magnetic field. Well, as a technical point, what was very interesting, I discovered that if you take a sandwich like this, or a magnetic multilayer, and you vary the separation of the magnetic layers, in this case by increasing the thickness of a copper spacer layer, you would see these beautiful oscillations in the magnitude of this giant magnetoresistance as one increased the separation of these magnetic layers. And these oscillations reflect a long-range magnetic interaction of these magnetic layers through this spacer layer. The spacer layer itself becomes slightly magnetic, leading to magnetic coupling of the layers, so that in zero field they want to be coupled either parallel or anti-parallel, but this will oscillate as one increases the spacer thickness, in this case copper, by just a few atomic layers. And you can see here in this bottom part of this foil, we can actually create structures which are crystallographically oriented in different directions, and then the oscillations of this phenomenon will change. This reflects the intrinsic electronic properties of this copper itself. Well, it turns out this long-range magnetic interaction is extremely important in building useful technologically relevant devices. So this tries to explain to you how this basic phenomenon works. If you take a material like copper and you introduce a magnetic atom, the electrons in the copper will respond. They become slightly magnetic, but because their response is incomplete, then the electron spin density will oscillate on the atomic scale, and this means that magnetic layers, depending upon their spacing, will respond so that their moments will be, as I said, antiparallel or parallel. In this way, this is shown in this cartoon. It depends on how many wave functions we can fit within the copper layer between these magnetic layers, as shown here in the bottom part of this foil. So what is the use of this? Well, first, again, one could show that this long-range oscillatory coupling is actually common to nearly all non-magnetic elements in the periodic table. And one can see here how the magnitude of this strength of this interaction increases as you move across the periodic table in this way, as you basically introduce more electrons into these metallic layers. One of the most important elements, it turns out, from a technological point of view, is something called ruthenium. And ruthenium gives rise to an extremely strong antiferromagnetic interaction of two magnetic layers when they're separated by a ruthenium material layer, which is only 2 or 3 atomic layers thick. The interaction is so strong, it would require a field to reorient these magnetic layers of many tens of thousands of times the Earth's magnetic field. So using this phenomenon, we can actually build now a useful, technologically relevant spin valve sensing device. And so on the left-hand side, you can see what we do is we create this sandwich of 2 magnetic layers separated by copper. The copper here is shown in this copper color. And we have to fix the magnetic moment direction of one of the layers in the sandwich, which we do by coupling this to an antiferromagnetic material. This was a phenomenon that was discovered in the 1950s. But by itself, this is not a useful device, because on the atomic scale, these little magnets in these layers, shown as these blue and red atoms, they give rise to magnetic fields at the edges. And these magnetic fields give rise to a very, very large coupling between the 2 magnetic layers, so large that now the system no longer responds to small magnetic fields. So what I invented was this concept that we could build a synthetic magnetic material in which there's no magnetization in this material. And we do this by taking these 2 magnetic layers shown here, separated by 1 or 2 atomic layers of ruthenium. So in net, we've built an artificial material with no net magnetization except at the surface. And since this scattering that gives rise to the magnetoresistance is from the interfaces, from the surfaces, we can still see significant magnetoresistance, but we eliminate this magnetic interaction, and this essentially is the structure that was used when we introduced these materials to read information in a magnetic disk drive. So this is a technological, a little bit about the underlying physics of a spintronic material, and you can see what we have to do is create these unnatural materials by building them really 1 atomic layer at a time, and this was possible using the techniques that I briefly mentioned. So now we look at how we use this really fundamental discoveries of giant magnetoresistance, long-range oscillatory coupling, interfacial scattering, to build a spin valve sensor for a disk drive. And the way a disk drive works, as I mentioned earlier, is that you have a magnetic layer shown here, and this magnetic layer is magnetized so the moments are pointing in one direction or the other. And the boundaries between these magnetic layers, that's where we store a 0 and a 1. It's either the presence or absence of this boundary. And then above the surface of this magnetic film, which is deposited on a glass disc, we fly what's called a recording head. It's a small ceramic object. And today it's flown just a few atomic layers above the surface of this magnetic film. And on the backside of this ceramic object, the recording head, we build a spin valve device. And then as this head is flying over the rotating magnetic disk, it can detect tiny magnetic fields that are emanating from the boundaries between these magnetic regions. and then these fields will give rise to a change in resistance of the spin valve sensing material, and so we can detect these transitions. And this, as I said, because of the sensitivity of this device, we can detect tiny regions which were about 1,000 times smaller than was possible before. So this then has led to an enormous increase in the storage capacity of these drives. So here we could look at what is the number of magnetic bits or data that we can store per unit area as a function of time. And this graph is for a period of 50 years, the period of time for which IBM had first invented the disk drive technology and evolved it over a period of time. And if you look at the areal density on the left-hand side, you can see that during this 50-year period, the areal density increased by about 1 billion times. So that's an amazing development, essentially using the same concept over a period of half a century. And it reached a particular milestone in about 2003 or so, where we could store about 100 gigabits per square inch. That's the units used in the disk drive business, as the size of these magnetic regions was shrunk to smaller and smaller dimensions. So that's a very important time, because about that time we could, using a year's supply of hard disk drives, we could store all information that was known at that time in this year's supply of magnetic disk drives. So it's a very important juncture. At that point, we could store everything, all knowledge of mankind, in magnetic disk drives. So this gives you a glimpse into what a magnetic disk drive looked like. This is from a drive from 1962. It had 28 megabytes of storage capacity in 50 disks, but each disk was about 2 feet in diameter. And the total capacity, as I mentioned, just 28 megabytes. So but the basic concept shown on the right-hand side is a series of disks with magnetic films and the recording head between these disks. Now today, a modern disk drive can store about 1 terabyte of data in a single magnetic disk, only 2.5 inches in size. And so this is, well, I think that's pretty amazing in, well, a relatively short period of time, 50 years. So let's summarize. Spintronics, fundamental discoveries and a lot of innovation led to a new type of means of reading information in magnetic disk drives, and it really rapidly enabled a 1,000-fold increase in the storage capacity of these drives, enabling us to store essentially all knowledge. And well, I like to think this then makes possible access to all information, and because it's in a digital form, it's in its most useful form. And this then allows us to use Facebook and Google, and big data is only made possible because all that data can be stored and readily accessed in devices which are sufficiently cheap that we can do that at modest cost. So just in the last few minutes, perhaps I could touch on a couple of other technologies which are based on Spintronics that could have significant impact in the near future. And one of the first ones I'd like to briefly discuss is something called magnetic random access memory. This is built around a slightly different concept from a giant magnetoresistance, but the essential magnetic structures are the same. And in this case, as shown in this cartoon, we have two magnetic layers, the red and blue layers, and electrons now passed from one magnetic layer to the other through a very thin layer of an insulator, shown in gray. And when, again, the magnetic moments in this sandwich are parallel, current can readily quantum mechanically tunnel from one magnetic layer to the other. This is because the current itself is, again, strongly spin polarized. It consists of electrons with spins polarized in the same direction as the magnetization. Then these electrons can hop from one layer to the other. On the other hand, if we simply reverse the magnetic moments of one of the layers, then there are no longer states for the electrons to tunnel into, and the resistance is increased. But unlike the metallic spin valve devices, where the change in resistance is only about 10% at room temperature, the change in resistance now can be several 100% at room temperature. So this makes them even more useful. And this shows you how this technology, or these materials, have evolved over the last decade or so. And you can see that there's really been a dramatic increase in the magnitude of this tunneling magnetoresistance over the last 10 years, from essentially nothing at room temperature in the early 1990s to something approaching 600% today at room temperature. So these materials are useful for a number of different applications. Let me just briefly mention that. And one of them is this magnetic random access memory. This was something that I proposed in 1995. It's a long time ago. And essentially, it consists of a cross-point array. This is a series of word lines. These are nanoscopic copper lines, and a series of orthogonal bit lines, as shown here. And between every word and bit line, we introduce one of these tunnel junction devices. These are shown here as these gray regions. And by simply passing a current along a word line and exiting the current along a bit line, we can detect the resistance of this magnetic tunnel junction device. And a 0 and a 1 is recorded as the direction of magnetization of one of the layers in the device, whether it's parallel to a reference magnetic layer or whether antiparallel. The resistance will be high or low. So we can detect zeros and ones by simply passing tiny currents through these devices to detect their resistance. And on the other hand, in 1995, we proposed we could pass much larger currents along these word and bit lines, these copper lines, which we're using to access these devices, and the currents themselves generate local magnetic fields with which we could write the devices by passing a combination of two currents along a word and bit line simultaneously. And by reversing the direction of one of these currents, we could change the direction of magnetization that we were writing into the tunnel junction. So we could write a 0 or a 1 in this way. So this is the concept. So this takes advantage then of these giant tunneling magnetoresistance effects in these tunnel junction devices. Now these same tunnel junction devices can also be used to build even more sensitive read heads than the spin valve sensing device, although again the magnetic structures would be approximately the same. So these tunnel junction materials have been used in disk drives for about the last 7 years or so. So by way of reminder, a disk drive is a fantastic means of storing digital data very, very cheaply. But at the same time, there are certain drawbacks. Because it's a mechanical object that is rotated, then there's a limitation on how fast we can rotate this disk. And that limits the time taken to access the first bit of information. So basically it takes a few milliseconds to access a random bit of data in a magnetic disk drive. And at the same time, these devices are, as I said, slow, a little bit unreliable because the recording device is floating above this disk at just a few atomic layer spacings in operation. So that means sometimes there's a mechanical failure and you'll simply lose all the data in your disk drive. This can be quite annoying. Now, on the other hand, I said we could use this tunnel junction to store zeros and ones in this memory. And we could build a non-volatile memory in this way. And this, we've actually achieved this. We proposed it in 1995. We've built several generations of these memory devices. This is a 16 megabit memory chip which uses these tunnel junctions to store data. So it's possible. And it has some very nice attributes. It's extremely fast. We could read on the scale of nanoseconds. So it's 1 million times faster for reading and writing than a magnetic disk drive. And there's no problem with mechanical failure because there's no moving parts. At the same time, like all conventional memory technologies, it's relatively expensive. To store one bit of information is about 100 times more expensive than storing a bit of information in a magnetic disk drive. So after IBM sold its disk drive business in 2002, I proposed we could replace magnetic disk drives with an entirely new spintronic device, which I called a magnetic racetrack. And the concept here is that in order to overcome this price advantage of a disk drive compared to solid-state memories, what we need to do is store 100 bits in the same area of a conventional memory as is possible today. And we can do this by building this racetrack, which consists of a magnetic wire, shown here, vertically above the surface of a silicon wafer, And the wire contains magnetic regions, and again, information is encoded in the presence or absence of these regions or the boundaries between them. But the new concept is that simply by passing a current into this wire, we could move the magnetic regions around the wire and bring a particular piece of information to a reading or writing device at one point along this racetrack. So in this way, we could improve the density of a conventional memory by 100-fold, and therefore reduce the cost by 100-fold. So we could then build a device that could be as cheap as a magnetic disk drive, but would be 1,000,000 times faster, would never wear out, totally reliable, no moving parts. We don't even need to move a single atom to make this work. And it uses this new spintronic concept of manipulating magnetization by simply passing current into the magnetic region. And this is shown in this cartoon. So I mentioned, you pass a current into a magnetic material, the current is carried by electrons of one spin orientation. Well, it turns out a current of spin-polarized electrons carries spin angular momentum. And when you pass that current into or across a magnetic boundary, such as is shown here, the magnetic boundary will move because the polarized electrons can transfer that angular momentum to the magnetic system. And in this way, we could move all the magnetic information in the racetrack systematically shifted in one direction or the other direction by changing the current. That's a very, very simple concept. And that's something that we've demonstrated then in the last several years. This works. We built a prototype of this memory. And in principle, we should be able to achieve, using this three-dimensional racetrack concept, we could build a solid-state memory with the same capacity as a magnetic disk drive, but in a much smaller form factor, much more reliable, 1,000,000 times faster, and use much less energy. So it sounds extremely good. And if we simply build racetrack horizontally, we could replace flash, which is the one of the major conventional charge-based memory devices today. But again, we would be faster, much more energy efficient, and totally reliable, unlike flash memory, which wears out after you've written the memory about 100 times today. Well, this is a microscopic view of one racetrack memory, and here is a nano wire, and you can see 20 of these magnetic regions which were moving backwards and forwards by simply passing nanosecond-long current pulses into this wire. So we can move these magnetic informations at about 1,000 meters per second, very, very fast, with relatively small current densities, and we can make these regions very small on the scale of a few nanometers. So in principle, we've understood in the last few years how to take this very fundamental concept of manipulating magnetization with currents of spin-polarized electrons. We've used it to build and demonstrate a really interesting concept for a new memory storage device that could replace essentially all magnetic disk drives, nearly all forms of conventional memory, and make computers that will be more compact, smaller, and much more energy efficient. And this is based on very, very interesting recent developments in Spintronics that we and others have shown. So I'm almost coming to the end. So what I wanted to say then was that Spintronics has, of course, enabled this digital revolution in the last 10 years by enabling us to store essentially all knowledge in magnetic disk drives that we can then access through the internet. Now, magnetic disk drives, like conventional silicon-based charge-based electronics, are fundamentally two-dimensional in the way they're constructed. And I think what's going to be very important in the future is building devices that are innately three-dimensional. And I think racetrack memory is a very interesting concept, which is innately three-dimensional, goes beyond a single layer of transistors or a single layer of magnetic bits, and could enable this possibility of enormously increasing the storage capacity of conventional solid-state devices. Would make it extremely interesting. And my other area of interest, which I don't have time to discuss, is the possibility of building entirely different types of devices for computing applications, what I call cognitive devices. And in this sense, the goal here would be to build computing devices that could compute 1 million times more efficiently than today's computing devices. And we know, by example of the brain, that the brain can perform computing operations about 1 million times more energy efficiently than today's silicon-based computers. So I think this is a very exciting area of research where the development of new materials and new devices with what I would call cognitive attributes will enable new, highly efficient computing devices. So I'd like to end and show you, hopefully, a little glimpse into the field of spintronics and how, by manipulating currents of spin-polarized electrons, we can build, not only we've already increased storage capacities of magnetic disk drives 1,000 or 10,000 times. We've proposed and demonstrated new forms of solid-state memories, which would require no power to maintain their memory by using magnetic tunnel junctions. And using this concept of manipulating magnetic moments using spin-polarized currents, I proposed and demonstrated racetrack memory, which promises a universal type of memory storage device that I think could have enormous impact on computing technologies in the future. So I'd like to thank you very much for your attention, and of course I'd like to thank the Technology Academy of Finland for having awarded me this amazing and wonderful Millennium Technology Prize. Thank you very much for your attention.